So in this class, let us discuss some more applications in Gauss law. First, numerical application. The electric field is given by 6I cap plus 3J cap plus 4K cap. We need to calculate the electric flux through a surface of area 20 units lying in YZ plane. Okay. Your electric field is given by 6I cap plus 3J cap plus 4K cap. And you want to calculate the electric flux through a surface having area 20 units lying in YZ plane. So your area vector will be in which direction? Since your surface is lying in YZ plane, so your area vector will be on the x-axis, and x-axis, the direction of the x-axis is represented by I cap. So the area vector will be 20 units in the direction of x-axis I cap. Now we want to find out the electric flux over this surface. So electric flux over the surface is given by E dot ds, or simply instead of ds we have E dot s, ds Java ds. Okay? Your E is 6I cap plus 3J cap plus 4K dot s 20I cap. Right? In vectors we know that I dot I will be equal to 1, J dot J will be equal to 1, K dot K will be equal to 1. But I dot J will be 0, J dot K will be 0, and I dot K also will be 0. Seriously? I dot I will be 1, J dot I will be 0, K dot I also will be 0. Right? So since I dot I is 1, so 6 into 20, 120 times 1, I dot I is 1, right? Since I dot I is 1, so 6 into 20 is 120, right? So your electric flux is 120 units. Is it okay? So electric flux over that surface having this much area due to this electric field will be only 120 units. Clear? Okay. So coming to question number 2. An infinite line charge produces an electric field means electric field of 9 into 10 to the power 4 Newton per coulomb at a distance of 2 centimeters from it. You have to calculate the linear charge density. So suppose this is your infinite line charge, right? At a point, say P, which is at a distance of 2 centimeters, the electric field is given to be 9 into 10 to the power 4 Newton per coulomb. We need to find the linear charge density. Now, in the application of Gauss law, in the previous video we have seen that the electric field at any point due to a line charge is given by what? Lambda upon 2 pi epsilon naught into r, where r is the distance of that point from the line charge, right? We want to calculate lambda now. Yes. So in order to calculate lambda, we need E. E is given to be, your electric field is given to be 9 into 10 to the power 4 Newton per coulomb, right? The distance is given to be 2 centimeters. So 2 into 10 to the power minus 2 meters divided by 100, that is in meter. Okay. And then we need to know the value of epsilon naught. See, value of epsilon naught is 8.85 into 10 to the power minus 12 coulomb square per Newton per meter square. Okay, that is epsilon naught. But instead of using that value, see, we know that 1 by 4 pi epsilon naught, in Coulomb's law we studied that 1 by 4 pi epsilon naught, the value is equal to 9 into 10 to the power 9. No? But here we have only 2 pi epsilon naught. We can make it to 4 pi epsilon naught. How? E is equal to, you just multiply here by 2. Okay, what I can do is lambda upon 2 pi epsilon naught, just write it as 4 pi epsilon naught, right? And then you multiply by 2 in the numerator. So 2 times is 4, same thing. Now this is, I'm going to rearrange this one. 1 by 4 pi epsilon naught into 2 lambda upon r. Right? Is it okay? Yes. Now, your E is given to be 9 into 10 to the power 4, right? 1 by 4 pi epsilon naught is 9 into 10 to the power 9 Newton meters square per coulomb into 2 lambda. 2 lambda is unknown. Your R is 2 into 10 to the power minus 2. Here 2 cancels out. So 9 into 10 to the power 4 is equal to 9 into 10 to the power 9 plus 2 times lambda, right? So 9 into 10 to the power 4 is equal to 9 into 10 to the power 11 times lambda. So your lambda, 9 into 10 to the power 4 upon 9 into 10 to the power 11 will be lambda now. So 9 cancels out. So in that case, this implies 10 to the power 4 minus 11 will be equal to lambda. In that case, your lambda will be equal to 10 to the power minus 7. Is it okay? Lambda will be 10 to the power minus 7. And linear charge density. So it will be Coulomb per meter. Coulomb per meter. Because linear charge density is defined as charge per unit length. Is it okay? So it will be Coulomb per meter. Q is Coulomb. L means meter. So Coulomb per meter. Unit of charge is Coulomb. Unit of length is meter. So Coulomb per meter. Is it alright? Okay. Now question number 3. We have a spherical Gaussian surface. Okay, which encloses a charge of 8.85 into 10 to the power minus 8 coulomb. You need to calculate the electric flux passing through the surface, right? Okay. From the definition of Gauss law, we know that the electric flux through any closed surface enclosing a charge is given by 1 by epsilon naught times the charge enclosed, right? Here your charge is given, the magnitude of the charge is given to be 8.85 into 10 to the power minus 8 coulomb. And the value of epsilon naught is 8.85 into 10 to the power minus 12 coulomb square per Newton per meter square. Okay, that is the value of epsilon naught. So 1 upon epsilon naught means 8.85 into 10 to the power minus 12. Okay. We need to write the unit here into Q. Your Q is 8.85 into 10 to the power minus 8. Okay. Then what do we have here? 8.85 cancels out. So we have 10 to the power minus 8
plus 12.
plus 12. So the electric flux will be 10 to the power
4.
10 to the power. Is it okay? Yeah, units. Okay. I think that's it. No? The unit for electric flask. What will be the unit for electric flask? See? Q means coulomb, right? And E naught means C square per Newton per meter square. Not coulomb square per Newton per meter square. Here 1 coulomb cancels out. Newton to the power minus 1. If you bring to the numerator, it becomes Newton. Per meter square becomes meter square and per coulomb. No? So we'll write Newton per coulomb. Newton meter square per coulomb. Newton meter square per coulomb. Is that alright? That should be the unit for electric flask. Yeah.